motion, the vibration is known as heat. So what happens to these little passageways in between when these things start to vibrate? Notice that those little passageways will start to diminish because of the vibration. As a result, what happens, the electrons will feel much more resistance. So it's going to impede the motion of these electrons through the structure when the molecules are vibrating faster and faster. So that's what happens. Okay, by the way, average kinetic energy of these vibrational molecules, vibration and rotation of these molecules known as temperature. All right, so which means the temperature goes up. So as the temperature goes up, what happens? Temperature goes up, the resistance is going to go up. Because those passageways between the atoms and the molecules will start to diminish. It becomes smaller and smaller and smaller. All right, so temperature is the other contributing factor. All right, so resistance is going to be directly proportional to temperature. The reason is because resistivity is directly proportional to temperature. All right, so with resistivity, what's going to happen is with temperature, the resistivity is going to increase. All right, there's an expression. Okay, we'll cycle back to that expression. I don't want to worry about it right now. Something that we will discuss in depth later. Right, so the resistivity is the major contributing factor for resistance. It's how much the atomic structure inhibits the motion of these electrons. How much the atomic structure impedes the motion of these electrons. Atomic or the molecular structure. All right, so the contributing factors for resistance, once again, is the material itself. So we're dealing with the atomic or the molecular structure of the material. So the larger the resistivity is, the larger the resistance is. The length is definitely going to increase resistance. And the thickness is going to reduce resistance. And the temperature is also going to increase resistance. All right, so those are the contributing factors.
Resistance to the progress of electrons. Just what is the nature of electrical resistance? Under the influence of an electric field, electrons move through a metal much as a marble falls through a viscous fluid. If it weren't for resistance, they would accelerate freely, like a falling body in a vacuum. But as it is, they move on the average at a constant speed. Resistivity is like viscosity. The more of it a material has, the slower a particle will move through it. But what slows the electrons down? In other words, in a conductor, what resists the flow of electricity? Inside a metal, electrons constantly move in all directions. Here, just a few of them are represented as dots. They orbit through the metal as if it were one giant molecule. This kind of flow encounters no resistance, nor does it create a net flow in one end and out the other. Under these conditions, the conductor is in electrostatic equilibrium. There's no electric field inside, no voltage difference from one end to the other. But if a battery makes an electric current flow, equilibrium is destroyed, and an electric field is created inside the conductor. Inside a perfect crystalline metal, if a sample of it could be found, the mobile electrons would continuously accelerate, like a penny falling in a vacuum. But in the real world, crystals aren't perfect. They have defects and impurities, and their atoms vibrate with thermal energy. Electrons, accelerated by the force of the electric field, bounce off each imperfection, behaving somewhat like a ball in a pinball machine. All that bouncing, all that stopping and restarting, produces the resistance that prevents the electron flow from building up speed. So the electrons move at a constant average speed, creating a constant current under the influence of a constant force. As the electrons bounce off the imperfections, they set the atoms into larger vibrations. So the electrical energy of accelerated electrons turns into the heat energy of vibrating atoms.
Okay, so what generates the heat? Meaning what sets the molecules into vibrational motion? Electrons colliding. All right, so the heat is caused by the vibrational motion of the atoms and molecules making up the structure. Atoms and molecules are vibrating because the electrons are colliding. That's it. All right, guys, take a break for 10. Be back within 10. Okay, so each and every single appliance that you will put into the circuit somehow is going to add resistance to the circuit. All right, so the appliances could be connected either in series, just like this, or they could be connected in parallel. So depending upon how they're connected, overall resistance either it's going to go up or it's going to go down. Okay, so just want to come up with some kind of a commonsensical conclusion for both of them. So resistors can be connected in series. So which means that you may have different appliances. You may have one single appliance here, so this is the amount of resistance that it's going to offer. You may get a second appliance, and you may end up getting a third one. Each and every single appliance is going to offer different amounts of resistance, and everything is going to be hooked onto the same voltage source in this case. So what happens to the overall resistance of the circuit? All right, so this is negative, this is positive. All right, so guys, the analogy that I'm going to get to use is going to work fine at this level. It's the traffic analogy. All right, so the current is going to represent the traffic flow, which means how fast the traffic is flowing. Okay. And then you hit your traffic right at this point, and then the traffic speed limit is 45 miles per hour, except the traffic is not moving that fast because this dumbass in front of you is texting, so which means that it's going to slow down. And next thing you know, somebody has a flat tire, so that's going to further slow down the traffic. And then you got a red light, it's going to slow down the traffic. Notice that every time there is something going on the road, someone is not moving at the speed limit, someone having a flat tire, and the red light is just going to keep slowing the traffic down more and more. All right, so when resistors are connected in a line like that in series, so what's going to happen is the overall resistance of the circuit is going to go up. That's what it means. So the overall resistance of the circuit goes up. So when they're connected in series, every single resistance will be additive. So it's just going to increase the overall resistance of the circuit. So what do we know? All right, so we know that the current is going to be inversely proportional to resistance. So which means that when the resistance goes up, the current is going to go down, which means that this traffic is going to slow down. All right, so the resistance goes up. So the overall resistance is going to go up, the current is going to go down. What that simply means is the charges are moving quite slow. So when the resistors are connected in series, traffic is going to slow down. All right, when they're connected in parallel, once again, each and every single device that you put into the circuit is going to offer resistance, and it's going to influence the current in the following fashion. All right, so we got these resistors, and they are parallel to each other, and all of them will be connected to a common voltage source. All right, so you got your common voltage source here, negative terminal to positive terminal, and the current is going up. All right, so it's going to hit a junction here. Part of the current is going to go in this direction, and then the rest of the current is going to go up. Part of the current is going to go in that direction. The rest of the current is going to go up. All right, so this is going to offer this much resistance, this is going to offer this much resistance, and this is going to offer that much resistance. All right, each and every single resistor is going to offer different amounts of resistance. So what happens to the overall resistance of the circuit when you actually hook them up in this fashion? Once again, we will get to use the traffic analogy. All right, so imagine that you're leaving work. That's a negative experience for you, and you're trying to get home. This is positive experience, or vice versa, depending upon what your situation is. The shortest route that you can take is this one, except guess what, guys? There's a bad accident. So this is going to offer a lot of resistance. You say, screw this. My life, my time is valuable, so you go up to the next one. Except this one is a red light, so the traffic stops and goes. So you're thinking this is not fast enough, so you go up to the next one. And this time the traffic is flowing actually okay. It's almost at the speed limit. This doesn't offer a lot of resistance. Notice what's happening. You're not stuck on the same pathway. It's not like this. This is the only route that you can take, and notice that the resistances are additive. Here, it's not the same. I mean, you could go up here, hey, it's resistance due too much. You say, okay, I don't want to waste my time here. You can definitely take this. There's a red light. Obviously, you're going to get there much sooner, but you say, okay, well, maybe there are no red lights, stop signs here. Maybe I'm going to go this way. All right, so you got all these options. So what's happening is, in this case, the resistance is going to be smaller. All right, so in this case, the resistances will be added reciprocally for reasons which will become obvious next week, I think, or not the next week, during the next chapter, we will cover this, I think. Okay. So what's happening is, so the resistance is going to, overall resistance is going to go down. So the current is inversely proportional to resistance. In this case, the resistance is going to go down. The current is going to go up. All right, so you got this inverse relationship right there. So the resistance goes down, the current goes up. All right. Let's talk about household circuits in general. All right, so I'm going to show you how I would design circuitry for my man cave. All right, given a choice, I would not do a design work like this because this sort of stuff is really time consuming. And most of you guys are engineering students, you would probably enjoy this a lot more than I would. Okay, I kind of like the theoretical stuff a lot more than hands-on stuff. All right, so if I had to design my own man cave, the way I would do it is I would turn it into a Faraday cage by using 20 miles long wires. All right, so when things are cheap, I would get my wiring, and then I would just wrap the wire right behind the drywall from ground to the ceiling. So I would turn this into a Faraday cage, okay? And then on the inside, you can do some physics experiments if that's what you want to do. So this place will be 100% lightning proof. Instead of conducting physics experiments, because this is my man cave, the most important stuff is the flat screen TV. So I would just set it up. Why would I do that, guys? Compared to you guys, I'm not as nerdy as most of you guys are. I still love to know.
Yes.
Okay, so we're on this right screen. All right, so I will put my TV up here. All right, so in front of the TV, I'm just gonna get my couch. Awesome. And then right next to it, the dog bed, man's best friend. Because it's a man cave, I just want to make sure that it's only for me and for my dog. And you know, it gets kind of cold during the winter, so I don't want to go out. So what I'm gonna do is I'm gonna put a fire hydrant right here. So the dog could pee here, all right? And then it's just gonna leak out, that's perfect. I'm a computational physicist, so I need my computer. I work on artificial intelligence, so I'm just gonna place my computer here, desktop. I got the laptop usually right on me. And then you need to have a fridge. That's where the beer is. You need to keep it cold. So beer if you're a guy, ice cream if you're not. So you got your stuff right there. All right, the easiest way to wire this, and this is what most people would try to do, is the following. Easiest way to wire it. This is what we're gonna do, lazy way of doing it. All right, so this is gonna be, the current is gonna come in, it's gonna go through the computer, and then it's gonna go through the TV, and then it's gonna go through the fridge, and then it's gonna come out. Beautiful. All right, so you go home. All right, so you turn on the computer, whatever it is that you do, check email or whatnot, turn on the TV, have fun, and then get your beer, and everything is fine. All right, life is finally making sense. At some point, you will have to turn off the TV. So what happens when you turn off the TV, guys? As soon as you turn off the TV, there's no current. The computer is not going to work. Fridge is not going to work. So what happens to the beer? It gets warm. What happens to the ice cream? It's going to melt. If you connect things in this fashion, guys, everything is connected in series. So what happens is if you turn off one of the appliances, it's going to offer infinite resistance. So the rest of the circuit is just going to shut down. So this is what happens. And the problem with this kind of wiring is, though, it can also cause electrical wiring. All right, the resistance may go up too much, and then next, boom. If that's the case, in order to protect your valuables, you need to have a fire hydrant somewhere. You're not going to be able to put out the electrical current, but at least this couch is going to be safe, the dog bed is going to be safe, so that's the extent of it. All right, so that kind of wiring does not work, right? So what you need to do is, in the house, the structures usually, the residences, are usually connected in parallel. All right, so this may be your TV. You can turn this off. This is the fridge. There's still going to be current going through the fridge, and there's still going to be current going through the computer. So household appliances and household devices or electrical setup of the households are usually done in parallel. All right, so household circuits are connected in parallel. So you can turn on and off the appliances without turning off the entire circuit. All right, so this brings us to the point of electrical power.